We're going to start today talking about the topic that I have great interest in, is the use of nanotechnology and textiles. We have been doing this for almost 12 years. And this idea of making what is very small, merging that with something that is really large. So to give you an idea of the sizes that we are looking at, for example, if you know about a 6-year-old kid is about 1 meter tall. Yeah, this is 1 meter. In the US, we don't use meters, but in Canada, you use. So you divide that by 10, you get about the width of your palm. It's about 10 centimeters. You divide that by 10, you get about the diameter of your pinky. Yeah? And you divide that by 10, you get maybe 1 millimeter, which is about like a freckle. You divide that by 10, and you get in the order of a hair, 100 microns. You divide by 10 again, and then you get in the order of bacteria, and you divide that by 10, and you get in the order of blood cells. And then you divide by 10, then you get in the order of viruses. And then you divide by 10, and then you are in my domain. That's my domain. Very, very small. So many things happen in that domain. One of them is light is much bigger than the objects that we look at, so you cannot see them with the optical microscope. The concept of color doesn't exist. And materials behave very differently in that domain. And that's what I have great fascination for that. So I'm going to talk about multifunctional fibers via manipulation of nanoscale phenomena. And these are my students. And at the end of the talk, I'm gonna tell you the story of all these dresses and how they actually are a combination of science and design. And that's an area that I have great fascination. So first, I want to say thank you to the people that sponsor my research. So these are the Department of Homeland Security, Department of Commerce, National Science Foundation, Fulbright, NISTAR, Department of Agriculture, and the Swiss National Science Foundation, the Chubu Foundation in Japan, and many other agencies, the Science Without Borders in Brazil. So I'm very grateful, and also I told you this morning that I was a fan of Formula One, yeah? So in Formula One, the size of the logo is proportional to the amount of money that they give you, yeah? So here is the same. So those who give me more money have a bigger logo. But all of them are welcome, all of them are welcome. So everything I'm going to talk to you about is going to be in this website that probably you visited before you came. And these are my students that you will see on Friday. These are the people that make the magic happen. And they are coming from different countries, from Switzerland, from Turkey, from Colombia, from Brazil, from Israel, everywhere. And different backgrounds, chemists, physicists, material scientists, chemical engineers, textile engineers. We are a great believer on multidisciplinary work. So in 2002, I obtained my PhD in chemical engineering. And it was a very difficult time to find a job. So I decided that if I could not find a job, I should be in school. And then decided to go for an MBA. But when I went to an MBA information session, I was presented with this graph. And this graph, it shows you that every 50 years, there is a revolution. And this revolution is based on knowledge. New knowledge is created, and this knowledge creates money and new industries. And it happens every 50 years. And then the person that was talking about this from Merrill Lynch was talking about the first one came with textiles in the 1700s, 1800s in England. And that the idea of using steam to produce faster and larger amounts really made the Industrial Revolution happen. And those beautiful canals that you have in the middle of England are an evidence of that. You have, those were the internet of the 1700s, those canals. And then 50 years later came the railroad revolution, And that was totally different too, because people used to live, die, and pretty much live your life about 40 miles around one single point, the point you were born. Yeah, you have no, you didn't want to move to other places. The concept of going to work didn't exist. Yeah, you work in the same place where you were born. But now with the railroad, you can work anywhere. You can go anywhere, as far as there is a railroad. Yeah. So that changed this idea of transportation. And then at the beginning of the century, 50 years later, came the automobile that changed also the paradigm. We are now not talking about moving with a lot of people in the railroad, but moving individually, like as an individual. And now you can see that these developments are moving from Europe to the US, yeah, and moving east, yeah. So these knowledge-based economies are moving east. Then came the computer at the beginning of the World War II. You probably watched the movie, the Enigma. Did you watch the movie? Okay. And then a new generation, but this was even more powerful because before we could multiply our muscles. We could make things faster, we could make things in larger amounts. But now with the computer, we can actually multiply our brain. We can process information much faster. And that's because that's the reason some of the developments in science in the last 60 years have been astronomical. We have learned much more in the last 60 years than thousands of years before because now we can process information to the point that now we cannot access all the information. Even if we want to access all the books, all the articles, that's not possible. Yeah? And then that person talked about nanomaterials at the end of 1990s, in 2000s. And it came to say, well, can you actually merge these two things together? Something that is 200 years apart, something that is old and traditional like a textile, and something new and revolutionary like nanomaterials. And that was the premise that I decided to use for my career. It was very difficult to pursue because most people thought there was no connection. And even sometimes I thought myself that there were no connections. Because they are so different, they work at different scales. Textiles, you work on thousands of yards produced per day, and in nanomaterials, you are talking about atoms and molecules that you can deposit in small areas. But that was the premise of my academic work. And when I moved to Cornell, I was very happy because Cornell has been working in the area of nanomaterials for almost 37 years. That's a long time, yeah? So we have 4 centers, the Nanobiotechnology Center that combines nano and biology, the Nanoscale Science and Technology Facility, the Center for Nanoscale Systems, and the Center for Materials Research. And all the information is in the links that you can see there. So people at Cornell have been working on these issues before. I just added a new one, which is the area of textiles and clothing. So I do my academic work in 3 areas. One of them is modifying existing materials, mostly cotton, using nanomaterials, and that's what I'm going to talk to you today. The second area is creation of new materials, using new phenomena, electrical, magnetic phenomena. And the third one is the development of new metrology techniques, new ways to measure. As I told you before, it's very difficult to measure at these scales. So existing microscopy, existing techniques are no longer valid. So we have to develop our own, and that's the third area. But today in this afternoon, this session, we are only going to talk about the first part, how to modify materials with nanomaterials. And this is my inspiration. So these people are very popular, yeah? I told you I like cartoons, so here are my cartoons. Wonder Woman, Batman, Superman, Flash, Aquaman, Green Lantern. And I like them very much, not because of the concept of a cartoon, but also because they were developed in 1939. Superman was born in 1939. And they were developed before the war, before the US got into the war, and they have very unique characteristics. This is very, very American. The superheroes have superpowers that came from clothing, from their brain, from some tools. But so you can see, for example, Batman can stop the fire, Superman can stop bullets, Wonder Woman can have the lasso of truth, Flash can go really fast without being affected by friction. Now, what is interesting here is this is 1939. None of these materials existed in 1939. So most likely, Superman and Batman and Flash, they will have to dress in wool or cotton at that moment, because these materials did not exist. But that did not prevent the designer and the creator of these cartoons to think that maybe one day they will exist. And we should be very grateful that this designer, this cartoon designer, never talked to an engineer or a scientist at that moment, because they probably have told him, you are crazy. Why are you making these cartoons of things that do not exist? But now, 70 years later, these materials do exist. And I showed them some to you this morning. Yeah? You touch them, you wear them. And this is one of the examples in which design was able to inspire science. So scientists were inspired by this Superman cape and Batman and Flash. And so that was one of the cases when you have design driving science. Lately, we are moving in the opposite direction, which is having science, new materials, and then trying to inspire design. Yeah? Now, scientists and designers are very, very different. They are trained in a very different way. For example, scientists, when they have a big problem, what they do is they take the big issue and divide it into small pieces. And when divided into small pieces, try to solve the small piece. And then they think that by solving the small pieces, you will get the final solution. That's our illusion. Yeah? Now, designers operate the opposite. They can see the final solution. They can see how it's going to look the dress. They see how it's going to look the bridge, how it's going to look the piece of jewelry, how it's going to look the stadium. They may not know exactly how you're going to go there, but they can see it. They can see it at the end. And that's what they are so different, the way they think about the same issues. And our educational system trains people that way, in a very different manner. Like in mathematics, when you try to solve a differential equation, then the first one is you get the homogeneous solution, and then you solve for the particular cases. Yeah? You divide. Now, real life doesn't work that way. Yeah? So if you look at, for example, what is design and science, so for those of you who are mathematically oriented, that symbol before design is the symbol of the derivative. Yeah? And the symbol in science, this is the integral symbol, okay, summation. And just happened to work really well for this explanation. So a designer can see the final solution, can for example, get to this point and see how there are changes in that location, but information is very local. You don't know how to go there. You can see it in your mind. And the scientist takes the pathway, the final product, and then divide it into small pieces. Yeah? So one of them is a mathematical representation of a derivative, and the other one is the mathematical representation of an integral, which are totally opposite behaviors. Yeah? But they do work. They do work. And my job is to actually see if we can find an interface in which both types of behavior, of approach to a problem, may converge. Yeah? Now, to prove that, I use, this is my favorite molecule, is cotton. So cotton is my favorite material. Cotton it's a very old material, over 5,000 years old. And is abundant in many places in the world. So the science that I do here in Cornell may be applicable to the cotton in Texas, or the cotton in Alabama, or the cotton in Vietnam, or Sri Lanka, or Egypt, or Afghanistan. So that's why I like cotton. And also cotton tells the story of humankind. in some ways, yeah, I would recommend this book. It's the biography of cotton. It tells you how cotton, some of the major developments in history actually happened around cotton and textiles. Now, the first problem I tried to solve was a problem of protective clothing. And we talked this morning about that, how difficult it is to anticipate what are you going to be exposed to. So in this case, for example, you can be totally protected if you have a material that is impermeable. No air, no liquids, no vapors, no aerosols can go through. So you are protected, yeah, in a bubble. But you might not be able to breathe, yeah? So that may be a little issue, yeah? And you will be very uncomfortable. So you are protected but uncomfortable and you cannot operate. Now, one of the solutions is on the left side, and is to have a membrane of carbon that may be able to absorb some of these chemicals, so preventing them from being in contact with your skin, and allow you to breathe at the same time. But the price you paid is this carbon layer is heavy, yeah? So now you are protected, you may be comfortable, but you have to carry extra weight. Now, the next generation of materials will make that layer of carbon thinner, so it will be lighter. But what we want to do is to eliminate all that, and then make sure that we can have this material that can understand when something is dangerous, when something is not, allow it to go through or not. And that is a big challenge. So as I told you, for example, if you are a firefighter and going to an emergency situation, then you might be exposed to 100 chemicals. Imagine for a second that you have a T-shirt that protects you against one chemical. What happens if you wear more than one T-shirt? Anybody has tried that? What happens? You said what? Yeah, what happens? There's a thermal issue. What else? Yeah, movement is restricted, and there is issue of weight. So that's the issue. Now, what about if the T-shirt has the thickness of one single molecule? That may be a solution, yeah? So for do that, I use a process called self-assembly, in which I deposit molecules one on top of the other like a sandwich. So I put one that is a positive polyelectrolyte, one that is a negative polyelectrolyte, and I put them one on top of the other, and each one of them will be able to control a specific chemical. Now, this was a very challenging proposition because this method only worked for surfaces that were flat and they were homogeneous. The main issue is I wanted to use some cotton, which cotton is not homogeneous and is non-flat. In fact, the cotton from Alabama is different than Texas, and is different in July than in August because of fertilizers, because of weather. So you have to develop tools that will be robust enough to overcome all these issues. Now, when they tell you that things are not possible, that's when we like it more, yeah? Because that's a big challenge. We're going to make it happen, and we did. So here we have, this is the cross-section of a single cotton fiber, and it has 20 nanolayers on the outside. You can see them right there. And they go on a curved surface, yeah? So we submitted this to the journals, and as like anything new, the first thing that happens when you do something new, what happens?
Rejection.
Yeah, people don't believe you, yeah? Yeah? So you have to prove that this is actually true. Say, well, this is nice. Maybe you got lucky. These are 20 layers. We want to see one layer, yeah? So then after 6 months of and $50,000 in microscopy fees, we were able to actually image one single layer. So this layer is 20 nanometers. Remember the scales that I told you? 20 nanometers on top of the cotton fiber. And then we actually tested these materials against different gases, in this case, nerve gas and mustard gas. And we were able to prove how we can control the gases, how they move through the interfaces with these little layers of only 20 nanometers. So you are not changing the properties of the cotton. It's the same cotton. You just have adding this very small amount of polymers. Now, not only nerve gas and mustard gas, but also you can control how the humidity from your body gets out or doesn't get out. Some sports, you want all the humidity to get out really fast, and some sports you need a layer of water, yeah? So now we can control at what speed can they move. Now, so what I decided to do is, well, perhaps depositing layers of 1 molecule thick, that was fun, but why don't we just deposit layers that is 1 atom thick, much smaller, yeah? So we decided to do it much smaller, go smaller. So we use a process called atomic layer deposition. It's a very similar process to the previous one. We deposit layer by layer. But we use a very, very expensive chamber. We enter the precursors, there is a reaction, and we create the layers. This is a collaboration with Professor Parsons at NC State. And it was a lot of skepticism because this process can only work on semiconductors and transistors and integrated circuits. But now we try to do it on cotton, yeah? Yes?
So how do you solve the problem of cotton not being flat?
Okay, so the way we did it is we actually created functional groups in the cotton. So we create functional groups here that will work as an anchor and will trap the polymer in all points. So and we did the same for the atomic layer deposition. We functionalized the groups on the cotton, have the reaction with the metal, remove the excess, put water again. Again, we have OH, and then we can do 1 by 1. Except that this time, they are not 20 nanometers. They are not measuring nanometers. They are measuring angstroms. You guys remember how many angstroms in a nanometer? 10. Another division by 10. So now we're talking even much, much smaller domains. Yes?
Okay. You finally have got it down to an atom layer over cotton, which is basically molecular in its structure. And you attach it by metal, or what is the what is that level, that layer, how is it attached to the cotton? What is the...
Okay, so it's... No, there's no metal.
No, but if you get it, you've gone from a level of, that you put on of molecules, and then you get it down to atoms, okay? How do you attach that level of atoms?
Okay, so we have a chemical reaction between the groups that we put on the cotton and the precursor. So there is a chemical reaction. But the reaction is what we call saturated. Once the first layer is created, the second layer is not reactive.
Right, then you can build.
Then I can build 1 by 1, like a sandwich.
The first layer that I had the question about.
Yes, so we have to have a system that is self-saturated. Because if it's not self-saturated, it will build and will become thicker. So to give an easy answer, so we have cotton to be positive, and then we put a negative layer of polymer. And once it's negative, if you try to put another more negative, it will repel, yeah? So then you have to remove the excess and put the positive back again. And then you create layer by layer, 1 by 1.
So before you started the lecture, based on this morning, I had the basic question in my mind, and I had biology in mind, where the interaction of what you're doing, so far as I know, is molecular level. So you have a virus, and you look at the structure and their attachment points, etc. So what you're doing here is not molecule to molecule. You're really isolating by the substrate. You're isolating that cotton molecules, and then you're adding above it.
Correct. So we are about 10 times smaller than those interactions. So we are using the molecular control we have, but on large surfaces. And that's the beauty of cotton. So we made these layers, and these layers are only 50 angstroms. These are very, very small. And now we can have these layers, and they have a very large amount of thermal insulation. So you can have, in Ithaca, you guys remember when you were here, we have winters of -40, -30 degrees. You may not want to remember, but that's our case. But now you have enhanced insulation by using these very small layers. So maybe you don't need this 2 inches, 2-inch thick coat when you can have a T-shirt with 50 angstroms of coating. Yeah. So now this is a completely new way of thinking. And then I decided that perhaps these layers, as beautiful as they are, they may break because they are layers on the surface. So when you bend them, they will break. So we decided to move to objects that will be able to conform to the surface when they bend. So we use nanoparticles. So instead of a single layer, we work with individual particles. And we have the same process. We have particles, very small particles. We put them negatively charged. They assemble on the cotton and then create a layer, but the layer is composed of small particles. And then on top, I can put the next layer if I want.
But they're basically metallic, so you can
In this case, they are metallic, yeah.
And that gives you better control on the electrical charge.
Yes, yeah. I'm going to show you some examples when we did other type of particles, but these ones are metallic. And then, so this is a scanning electron microscope image. Yes? So what this scanning electron microscope does is they look at the surface, yeah? So it's looking at the surface, and then you can see the little particles here with the fibers, yeah? And then if I do a cross-section of that, then I use a different technique called a transmission electron microscope. So I see through. And then I can see the fiber of cotton and the particles on the outside, yeah? Almost single layer particles. And we did that for silver. And then the question is, okay, that looks beautiful, but how do you know that this little point is silver, yeah? So then we use a different technique called electron dispersive spectroscopy to verify that those little points are actually silver. This is the symbol for silver. So if you go to Argentina, Argentina is coming from this name because there was a lot of silver, argentum. Yeah. I was there last week. It's a fantastic place to visit. So then we deposit silver, we deposit gold. These are the gold particles and cotton. You can see them on the surface. And then here you can see them in the cross section. And this is one of those images that I tell my students that one image speaks 1,000 words. But people don't tell students is they need to take 1,000 images to find that one, yeah? That's the key. So here we have a single cotton fiber, the cross section, and you can see the different shapes, different topography, and we can place the particles one by one around. Yes, ma'am?
How do you chop a cotton fiber?
Okay, so I'm going to show you on Friday when we go to my lab. So we use a technique called ultramicrotomy. So we have the fibers, suppose this is the fiber, we embed it into a polymer, and then we use a diamond knife to cut. And we cut pieces that are only 70 to 80 nanometers, so the electrons can go through and see what's going through, what's happening through. So these materials are metal, so that the electrons cannot go, so that's why they are darker. And the cotton can go through. But you can also see that how the cotton grows layer by layer, yeah? Like humans, we grow like that. And then you can see the channels to the cotton distributes some of the nutrients. So this is a living entity. Cotton fiber is a living entity. You're talking about a natural material with a synthetic material. And that interface is something I love, yes?
What will that cotton be used for? Will it be used for shirts
Yes.
that people can wear?
For shirts, for
Will
dress.
it be cool like cotton?
It will be, you will not know the difference because this is so small, you cannot see the difference, you cannot feel the difference. It just behaves the same way that normal cotton.
Will you say 100% cotton on the label?
I would say 99.9999999%.
And how much would it cost?
Okay, so when I am, because I'm a professor, I can never say yes or no. Everything is a probability, yeah? And cost is not a variable in my research, luckily, but we think this will be in the order of a few $1,000s per square yard. But it's not, the issue is not the cost. I think I would like to think in terms of value. Because there are many functions for these materials. I'll show you later. How much will you pay for a t-shirt that will never make you sick? Or for a t-shirt that will tell you if you are going to be exposed to something that you are allergic to, or something that you don't need to wash forever, or will always be the same color. So these concepts are possible now. So this is gold, and now we're going to go to platinum here. And we also did platinum. So we did silver, gold, and platinum like the credit cards, yeah? And then we decided that we wanted to have a student that said, well, this process is not very efficient. You are placing the particles on the fiber. What about if we made the fiber part of the process? So we do a chemical reaction inside the fiber. These natural fibers have little porosity, so we can make chemical reactions inside. And say, well, let's do it. So we, instead of using the particles, we use what is called a salt. We inject it into the cotton, then we do a chemical reaction here, and the particles were created. Now, these particles don't look as beautiful as before, but they are on the surface of the cotton. They are a little bit bigger, not by much, but it's a process that is really, really, really fast. And then you can see them here. This is all gold too. And then you can see that the layers are a little bit thicker. But good enough, yeah? When we're talking about 10 to 20 nanometers, this is no big difference, yeah?
Basically cellulose.
It is cellulose, yeah. Cotton is, a high percentage of the cotton is cellulose. And then we decided to do all this, the same materials we did with the previous process. We wanted to do it here, but we couldn't do silver in this process. And we were trying to figure out why we couldn't do silver using that process. Until one of my students came with this idea and said, well, why instead of using positive cotton, we use negative cotton? And then she switched the polarity of the cotton. So through a carboxy methylation, this is a carboxy methyl group. And now you have a negative group to which you can put silver on top. So here is the result. We can have a large amount of silver particles that don't agglomerate in a surface that is non-flat and non-homogeneous. And that was fantastic for us because we knew this was big, but we didn't know what to use it for. So what is the first thing you do when you discover something big, but you don't know what's the use for? You are an attorney, you should know that.
File a patent.
Yes, because otherwise somebody else will find out what it's used for, yeah? So we filed a patent, and then we started looking for applications and see what can this be useful for. So one of the applications that we looked for was antibacterial, and then we look for Staphylococcus aureus and E. coli. These are bacteria very common, yeah? One of them is in hospitals, the other one is in food. And then we were able to kill 10 to the 7th. So 10 to the 7th means that of 10 million bacteria, 1 bacteria survives in contact with this one. So this is like 99.99999% efficiency.
But what is the killing agent? Is it silver itself?
It is silver. There's a controversy on what happens, but basically, what most people agree is silver ions interfere with the ability of the bacteria to reproduce. Yeah. So this was pretty good. We could do massive killing of bacteria. So you can put this material in, for example, mass transport. Yeah, in buses, metros, trains, airplanes, seats. How many people do you think sit in your plane seat before you sit?
Too many.
Yeah.
But also a lot of people have silver allergies. So how does that impact?
That is true, yeah.
Yeah.
Yeah, so that part I don't know yet because I'm only on the science part. But so there are many, many applications, no? Filtration for water in different domains. And then we look into different applications. These and other applications. This slide is a bit busy. So this is called surface-enhanced Raman spectroscopy. So we can detect very small amounts of compounds. So these particles so close to each other have an amplifying effect. So I can detect almost a single molecule present. So I can look at your shirt and tell you what you ate 6 months ago, or where you've been a year ago. Because those traces I can actually read and tell you, oh, you were in this farm, because this farm has this particular amount of this material. So this was very interesting. We could detect illegal drugs and also explosives with single cotton, single cotton. And then as I told you before, I work with designers. And then I have a student who was a designer. And then we started to explore how these particles, we can control the spacing between particles and the size of the particles. And we found that we could make color. So this color is not coming from dyes. It's not coming from pigments. But it's coming from the interaction of light with an object that is smaller than light, and controlling the spacing of the particle between particles and the size of the particle. So I can make particles of gold to look bluish or purple, or to look red. And even though my mother doesn't believe that that's actually gold, she says.
What is PD?
Oh, palladium.
Oh, palladium.
This is platinum,
gold and
silver.
okay.
So we can control the color in a physical way by controlling these interactions. So we can make pretty much any color without using a dye. And that probably will have been great for the science perspective, but I do work with designers. And then I have one designer, her name was Olivia. And Olivia saw these samples and told me one day, says, Professor, I like these colors. I wonder if I can make a dress from these materials. And the first reaction that came to my head was, this woman is crazy. Has no idea how difficult it is to place one particle next to the other and controlling the spacing. But when you are a professor, you never discourage a student with a crazy idea. Never. Because one upon a time, you also were the person with the crazy idea. So I told, Olivia, why don't we let's talk tomorrow. Let's talk tomorrow. Come back tomorrow. And actually, she came tomorrow. She came the next day. And then we worked with her on making these two dresses, in which all the colors are made with particles. Wow. They are not made with pigments. And then she wanted to show them in a fashion show. Now, Olivia worked with my chemist, and it was a very difficult process because the designers wanted just the material to make the creation, and then they have no interest in understanding the process. And the chemists have more interest in the process. So at the end, what I do is Olivia learned a little bit of the chemistry and got some sympathy to how difficult it was. And our chemists learn about fashion design and learn how difficult it is to think in 3 dimensions. It's not easy to think in 3 dimensions and take 2-dimensional objects into 3 dimensions. That's not easy. And then she went to a fashion show here at Cornell. And that was fun. So that's supposed to be the end of the story. But the next day, we have an avalanche of reporters in our lab. And everybody was excited about this combination of science and design. And Olivia was very happy because she answered many questions. She was in all the news that she wanted to be, in BBC, in CNN, in Popular Science, in The Telegraph, The Guardian. But the one that she really wanted to be was this one. You guys know which one is that? Yeah. Which one is that?
Women's Wear Daily, it's the main news source for fashion. If you're in that, you're set.
That is correct. That's the most important one. For scientists, it's Nature or Science, but for them, it's WWD. So she was there, she was happy, but in the process, I was able to realize that you could communicate science using fashion as a vehicle. So I could, if I go, I do a lot of outreach to high school students. If I go to a high school and talk to a student about the plasmonic effect and the size of a nanoparticle and how the radiation of wavelength of light hits an object that is smaller than the wavelength of light, they may pay attention to me for about 10 milliseconds, yeah, before they say boring or. But if I tell them the story of a kid that designed a dress and that the color of the dress is coming from these effects, I may have a chance that that student will pay attention to me and get interested in science. So that was a learning lesson for us. Then the next thing that we got to visit was, well, what about if you can create color, can you make color disappear? It's the same concept. That's what we talk about the near infrared. So I can place the particles in such a way that I can make the near infrared radiation actually disappear or move. Yeah. So you will look at the movies, the old movies from Rambo and the war movies, people have these night vision goggles, yeah? So an object that is dark then becomes green, yeah? And the reason it becomes green is because you take photons, convert them into electrons, and then you bombard them into a screen of phosphor, and then you can see the same image augmented. And the camouflage that we saw this morning has 3 colors. So we have ways to create optical filters by controlling the spacing of the particles and how we place them on top of each other. So my student was able to take these colors out of the range of visibility. So this is the range of visibility, just by using particles. And the particles were so close to each other that you can make little pockets of air between particles that prevent these materials from being wet. No liquids, no oils can go through. So nothing gets wet. So you put oil, bounces back, water, bounces back. And it was nice, but we didn't say, well, it's nice to have materials that never get dirty. But what I really want to do is to transfer one electron between particles and particles. And we were not able to do it because you could not do chemistry. The material doesn't get wet. There is no way to do chemistry to conduct, yeah, without water or organic solvent. Until I have a student that came from Italy. We can do all these coatings. And my student that came from Italy, he was an electrical engineer. So I told him, okay, you can help me get this done. And then he tried many ways and didn't work. Until one day he says, you know, I noticed that these materials don't get wet, but the air goes through. And so why don't we do a chemical reaction in air? And that's when I say, it's a chemical reaction in air. This guy is crazy, man. The thing is not possible. But of course, he's not a chemist. He's an electrical engineer. There's no chemical reactions in air, don't exist. So I said, well, Giorgio, you know, you should come back tomorrow. And then
Then he came back.
yeah. And in the process, I realized that what he called air is what I call vapor. So we were talking about exactly the same thing, but with different terms. And then so we decided to put a catalyst on the particles and then inject the reactants as a vapor. And then create these bridges between particles with a polymer. It's a piece of flexible material that can conduct the electricity between particles. And it works. So you can make things like conducting electricity using cotton that can be sewn and can be bent, can be wrapped around, because it's 99.9999% cotton. It's real cotton. Only thing is we cover the last 5 nanometers. And here it is, another example. You can make a knot. We wanted to show that it's flexible enough that it's like a normal piece of cotton, except
It won't burn because there's cotton.
it will burn, yeah. I never thought about that. Yeah, it's pretty much cotton. It's just, we just modify the surface. Yeah. So this was good. We were able to do this conducting electricity. And then we have a designer that came to my lab. And then she looked at these experiments. And the same story. She said, oh, professor, this is so nice. I would like to make a dress from this material. And then it was the same story. Yeah? You know, her name was Abby. She says, you know, okay, Abby, why don't we just come back tomorrow? And then and we think about how to do this, how to combine this, because at this moment I can only make threads. I cannot make fabrics at that moment. So think about the threads, how we can use it. And she was very clever. She actually made a dress, and then she put solar cells on the dress. And then at the same time that she was sewing the dress, she was connecting all the electrical circuitry with the same thread. Yeah? And then she got enough energy from the solar cells that she was able to charge an iPhone. So that was pretty clever. That was a very clever movement. Here it is. She graduated. Yeah, Abby Liebman.
Oh, she's
You know her?
friends. I didn't realize she did.
Oh, she's brilliant. When you see her, say hello.
Oh, yeah, I will. Oh, my God. Okay.
Is she was going to do a master's, yeah?
No, she's in New York City. She was designing shoes for a while, and I forgot exactly where she is now, but she's doing really well.
Yeah, well, she's very, very
Yeah, she's
clever,
awesome.
very smart. So yeah, this was Abby. And then we decided, well, conducting electricity is fun, but why don't we just make something more difficult? Why don't we just make this a transistor from cotton? Yeah, and that's a crazy idea. So they say, well, Giorgio, let's make a transistor of cotton. And at this moment, when he said that, so well, let's go for that. We don't have to come back tomorrow. You just do it. And this was very clever because then there were two types of transistors: an electrochemical transistor and a field effect transistor made from pure cotton. So no silicon, like most of the transistors on your phone or computers. This is made of cotton. So imagine that you can have in every intersection in your clothing, you have hundreds of thousands of intersections, millions. Each one of those can be a transistor. Yeah. Then you can have a computer made of your clothing, and it's flexible. Instead of attaching the electronics to the clothing, you actually made the clothing the electronic. Yeah? Now, we thought this was great and brilliant, except that 500 years ago, some people thought about that. And they were the Incas in Peru. So they have this device, and they can do calculations using knots and threads, like a calculator. So what we want to do, this object is called a quipu. What we want to do is to make a digital quipu using our cotton transistors to do major calculations. So that was a good experiment, and then we decided to move to particles that were non-metal. So in this case, we use carbon black particles, and silicon oxide, which are sand, pretty much sand. These are very inexpensive. And that's because black is one of the most difficult colors to make. So I can tell you that if you buy a black shirt and a black pant, they will never match. Is that right? Never match. Even if you buy from the same supplier, same store, they never match. Why?
They just have different absorption and reflective.
Yeah. The color changes with exposure to light.
Right.
The texture changes, so it's never black, the same black. But what about the tires of your car?
Same black.
They are always the same black, yeah? So we can use the same principle. So we can make these particles so small, these carbon black particles, and deposit them onto cotton, and then we can get these coatings that will be atomic level coatings of perfectly black bodies that will never fade, that will always be black, yeah? So if you look into this People magazine or these magazines that take pictures of famous people when they go to a theater, they use these huge flashes, yeah? And that light affects the color. But now, if you are like an A-star person, you have a tuxedo that looks always black. If you're like a B-star, C-star, the tuxedo looks reddish or bluish. And then they Photoshop, yeah, in the magazine. And those are tuxedos of $12,000, $15,000 a piece. So now you can have your perfectly black body that will never fade with only using these little particles. Now, we can also put the particles inside the fibers, so not only outside, but also inside. And that is very interesting to us because you can use the natural porosity of cotton as a chemical reactor. So if I want to deposit a particle that is this size, 10 nanometers, I can deposit here, 2 nanometers, and control the size using nature as an architect. Now I'm going to talk about these molecules that are probably the most beautiful molecules I came upon in my career. They are called metal organic frameworks. And these are molecules that are very unique because you can build the molecules like a cage. So this cage, this is the cage here, can capture a gas, and this yellow circle is a gas. And we can capture the gas and we can customize the size of the cage to the size of the gas. So we can capture this particular gas or this one.
How does the gas get into the cage in order to stay there?
Okay. So we have some chemical interactions between the molecule and the gas that will lure the gas to come, and then one stays there, stays there. And also you can later on heat it up, and then you can release the gas. These ligands could be flexible. So I'm very fortunate to work with Professor Yagi and Furukawa at the University of California in Berkeley, who invented these molecules. And our challenge was to place them into cotton. And that was a big, big challenge. We tried for almost a year and a half, and they didn't work. We could not put the particles on the cotton until I have a student from Brazil who was an expert in strawberry chemistry. And then she said, perhaps what you're doing is to attaching something to cotton. Why don't we do like people do in flavor chemistry? Instead of attaching to, you grow from the fiber. And that was a very clever move. So what she did is she deposited the copper and behaved like an anchor point inside the cotton. And from there, you build the molecule. Instead of building the molecule and attaching that, you build it from the base. And that allows us to actually create these materials that have cotton integrated with the metal organic framework, and then we can capture any gas by controlling the framework. So we are working with a metal oxide called copper oxide, and that has a very nice color, like a turquoise color. And so we're working with this, and we're getting these samples here. And this is the molecule we were depositing, until I have a designer, and her name was Jennifer. And then Jennifer looked at the samples and says, Professor, I would like to make a dress from this material. Yeah? And then I said, because I like the color. He says, well, Jennifer, it's not that simple, because the color is coming from copper oxide, but she was a physics major before she became a fashion designer. So she had interest in the physics behind. I said, why don't we, instead of just giving you the material, think of an application in which you can use this material and come with a design. And then she said, well, I like to run, but when I run, there is a smell from the cars, the exhaust of the cars, and my hair gets smelly. Why don't we just make a cup? I said, well, let's go ahead. And that's Jennifer. She's now working for Adidas. And then this is the cup, and this is the respirator that captured those gases. And that was interesting and then I have another student that says, well, it was nice that you captured something, but what about capturing and release? Can you do that? And I said, I didn't think about that. Why do I want to do that anyway? He says, well, see, I come from the Gambia, and many people in my family suffered from malaria. And then I have a postdoc from Kenya, and he says the same, yeah, malaria is very common, and we use these mosquito bed nets, but then the insecticide in the bed nets is released, then we are not protected anymore. So we would like to capture the insecticide and then release it when the mosquito is more active. And that was a very good project, because then my student and my postdoc decided to use these molecules to capture the insecticide in large amounts, so the mosquito bed nets will last longer without being refilled. And also, if you can make these ligands reactive to UV, then you can release the insecticide when the mosquito is more active. Instead of releasing that 24 hours of the time, you can release the insecticide depending on the light. Yeah. And that's what the student was actually built. So the bikini is not part of the dress, so only this part, the blue part, is where the mosquito is, the insecticide is captured. And now, one of the last things we are doing is, instead of placing particles, we are actually making wires. Because the particles, when you have abrasion, they may detach. But now we grow these wires like an anaconda. So it goes around and around the fiber. They're very, very small, a few nanometers. But when they go around and around, they give mechanical stability to the fiber. Yeah? And now these little wires can also have very unique signals. So we use quantum dots, but in this case they're quantum wires. And they have a very specific signal when you hit them with a particular laser. And then that signal can become a barcode, like a molecular barcode. So now you can know if you have a fiber like this, for example, in your purse, you can know if your purse is actually a Louis Vuitton or instead of a Louis Vuitton. Yeah? So I've been in many places in the world, and one of the places that fascinates me the most is called Shenzhen. Because Shenzhen, there is a shopping mall. What's the name of the shopping mall? Lowu. Okay, Chinos. So this shopping mall, you can find anything counterfeited, anything. And it's almost as good as the original. If you pay enough, they have different categories of how things are close to the original, like AAA, AA. It's incredible. They have standards for the counterfeiting industry. Yeah? So now, one of the main issues is if you can embed some of these fibers into the raw material, you might be able to trace where these materials are going, yeah? And see if this is original or not original. Because sometimes companies are asked by a designer factory to build maybe 100 of these items, and they make 120. So 100 back to the customer, and the other 20 go to the black market, yeah? So then you dilute the brand. There are many other issues. Food, yes?
So let me ask you, if I wanted to do a knockoff, I would go and get a copy of your patent, which you have filed to protect you in the United States, and then is it possible somewhere else to make these quantum wires and then essentially do knockoffs of the barcode?
That's true. But they will cost you more money than buying the original. And that's the real counterfeiting, when things are more expensive to copy than to actually buy it. Yeah? So why don't counterfeit this bottle? Because I can buy it for $1 in the other place, yeah? And also you need very specialized equipment and to make this. So it's not that trivial. Eventually everything can be counterfeited, yeah? If there is enough incentive.
But it is rocket science. You don't say it's not rocket science.
Yeah.
To reproduce, it is rocket science.
It is, at that level, yes. So we are very fortunate in Cornell. We have the microscopy, we have the techniques. That's not machinery that is easily available. Even if it's easily available, the people who use it doesn't have the expertise. But it's true, you know, some places in the world, they think that copyright is the right to copy. Yeah, that's the truth sometimes, yes.
So, sorry, are we, and maybe I missed it, a quantum wire as opposed to a coating? That's, to me, a whole different layer.
Yes, it's a different. So instead of placing the particles on top, now I place one particle, and then I grow the particle into a rod. And it wraps around the fiber. And I can control how many twists they do and how many times. So all this just by controlling phenomena at the nanoscale, at that small scale. So the last example I'm going to show you is, what about if we use the same molecules, the metal organic frameworks, but now we use materials that have that. Yes? Okay. These materials are able to actually react to different light. So we use europium, terbium, and gallium. And we do the same chemistry. We create the molecules, but now we have a different metal. Yeah, we have these. We could call them lanthanides. So we take a cotton fiber and we place these little nanorods. So the previous one, the nanorod was continuous. Yeah, these one are smaller, are finite. So very small nanorods on top, and then you beam light, UV light, into these objects. So something that looks white now suddenly has colors. Yeah, so we can make red with the europium. This is the powder. This is the cotton. We can make blue with gallium. This is the cotton fabric, and we can make green. So now we can make the three colors that compose the screens of your smartphones or your TV. Yeah. So if you look inside these little pixels, there are only three colors: red, green, and blue. Yeah. But we process information saying, oh, it looks yellow or green and orange. But now you can do it on textiles. So maybe you can use your clothing as a screen. Yeah. And then you can program to have the. I love the Tour de France, so I would like to watch the Tour de France here, and or have a screen that moves, gives me a color, or a flag that changes. So this is possible to do.
And the color is stable, it's not affected
Yes,
by
yeah.
UV.
I'll show you on Friday. So this is the sample how it looks under normal light, cotton. But if I put different wavelengths of light, then I can change the color to be red or to be green. And also gives you, I was talking to a philosopher, he says, well, this changes a lot of things in philosophy, because before we used to think that color was a property of an object, a characteristic of an object. This jacket is blue, yeah? But now, it may not be blue. It depends what light do you use to watch it. Now you might be able to control what color you want that to be. Yeah? I would like my wife to be dressed in yellow, so if she wears in green, doesn't matter. I can make it look yellow, just me, yeah. So then color becomes another variable that you can control instead of giving to you. Yeah. So these are the paradigms that I like to do, all the things that you can do with controlling things at a very small scale. Now, I talked to you about this issue of how different are designers and scientists, yeah? So designers work in this derivative space. You can help me because you're a mathematician. And scientists would like to work on an integral space, take everything, divide it, and compile. But luckily, they seem to be like they cannot be reconciled, except there is one function that operates the same under these two different conditions. And that function is the exponential function. Because the derivative of the exponential function is the same than the integral of the exponential function. And that's my challenge. How to find e to the x. The e to the x in design and the e to the x in science, and put them together. So what I've shown you here are examples of projects that are driven by students from Cornell that you know, yeah? That come with these ideas that are crazy enough, but at the same time require science behind, yeah? And we are very fortunate because we can make this combination of science and design and come with solutions to problems that will never be possible if only a designer would be doing that, or if only a scientist will be doing that. These solutions come because they are working in a very unique way, a very different way. And we are very fortunate in Cornell to have this type of students that are not constrained by their major. Yeah? You could be a government major and become a designer. Yeah? You could be a religious study person and become a computer programmer. The students don't see the limits. Now, our institution has limits, yeah, because we have departments, we have colleges, but students don't care about that. They care about making things happen. And we are very fortunate to have this type of students. And I'm a great believer in that, so we just keep moving our boundaries, and we believe that by modifying the small things, we can make bigger changes. All we do is do minor things. So with that, I want to thank you for your attention and for being part of this videotaping. Thank you very much. And you're going to see all these samples on Friday, on Wednesday, Wednesday.
Have you tried using other natural fibers such as,
Yes, so we use, I work with the University of the Amazon in Brazil. And I use a fiber called sisal that grows in the Amazon. And sisal, yeah. And it's a very strong fiber. You could see the natives carrying big animals with one single yarn, a huge animal with only one. And so you can use them for composites, and you can do chemical reactions. I come from Colombia, so we have a fiber called fique, and it's the fiber that is used to pack coffee bags. If you look at the commercials of Juan Valdez and his little donkey, he always has these sacks, yeah?
That's right.
And those sacks are made from that fiber. So we do chemistry on those fibers. We can deposit the particles, for example, silver or gold, make colors, but also kill bacteria. And one of the things that we have done lately is to be able to use these particles to decompose color. There are places in the world where you can find out what color is in fashion in New York or Paris by looking at the river. And that is a really sad situation, yeah? Oh, look, purple is fancy in New York, or pink, because they throw the dyes. I have seen those places like near Wuxi in China, yeah, and also in India, in Tirupur. And we buy those clothes in our stores here, but seldom we ask ourselves, where are these clothing coming from, or how they are made? So we are working with these particles to decompose those dyes using fique fibers as well. There is an initiative in Cornell called Agua Clara to have purified water to developing countries. So one of the ways you can do is, because everything is cellulose chemistry, you can place these particles using local trees from Guatemala or wherever you are on Morocco, and then embed the particles in those particular vegetation, drop it into a tank of water, and then you can kill the bacteria. So many applications. We never imagine. We focus on the science, on the fundamental processes, and then later on the applications will come. We like to think that way.
It'd be very useful in terms of space filters, water filters, the ready filters.
Yeah.
But if they have an actual chemical antibacterial effect.
Yeah, silver is an antibacterial.
What?
Silver.
Yes, that's right. And if it could be economical, it would be great for the milk nets, because everyone is in Asia.
Correct. And for example, when you go to a restaurant, how do you know that there is no E. coli on your table?
You don't.
Yeah.
So what about if you have a piece of cloth that you just go through, and then there's E. coli here, or Staphylococcus aureus, there is something here, or you clean it, yeah? So the other day I was flying to Abu Dhabi, and the gentleman next to me just sit down in the seat next to me with a box of Kleenex, and then he spent like 15 minutes cleaning the seat. He was a passenger, and then he told me, says, yeah, I don't trust these airplanes, and I got sick the other day, and that got me very scared too. But so he said, well, maybe we can make a better Kleenex for you, yeah? One that you can reuse and it can tell you information.
Antibacterial wet wipes doesn't work?
It worked, yeah. That's what he was using. But there are so many applications. There are many things that you don't know. I also work with some hotels. Some customers are very sensitive to bacteria, so they They want to make sure that the room is completely sterile. So maybe we can use this on sheets and pillows. Yeah. And these people are willing to pay significant amount of money more than the normal price for a hotel. So it's a lot of possibilities. We thought about painting. We can embed these particles in painting, so you can paint your home. So when your kids start touching things, they don't get bacteria. So there are many applications. We are great believers on that we understand the smaller things, the fundamentals, then we can find out the applications later on. We never imagined that we could make transistors from cotton or that Abby could make a solar cell dress. These things could come, but people that think differently, that come from different backgrounds, from different, grew up in different environments, have different education. Those ideas come from, because each one is different. So we see the world in a different way. And that's what I like working with designers. Last summer, 2 years ago, when I taught this class in Cornell Adult University, I was in Finland teaching chemistry, not to fashion designers, but to furniture designers. And it's the same molecule. Cellulose is the same molecule on wood. And I also work with people who does paper, the same molecule. So there's many applications. More questions? Yes?
Just one curiosity. Have you tried working with bamboo fiber?
No, not yet.
Okay.
But it's the same. Bamboo is also cellulose, and it's a wonderful
It's just because it's like in Asia, it's abundance and it grows really fast. So you can use all parts of the plant for all sorts of different things. And the other thing that we're trying is using the fiber to weave cloth.
Yeah.
It's been done actually. And it's quite soft.
It is very soft.
Yeah.
The only problem is the solvents they use to make the fiber are very toxic. So some of those fibers are actually illegal in the U.S. because of that, like viscose in the U.S. Yeah. So it's bamboo is a wonderful plant, and in Latin America it also grows. Called, what's the name in Latin America called? No, there's in Northern Uruguay. I saw it in Colombia. It's called caña, something caña, yeah. And it grows really fast. And then you can have all these very aligned molecules, and they use them to build houses and roofs. The same in Vietnam, and so that is something that we would love to explore. We need a crazy architect to come and tell us how we can do it. But there are so many possibilities, yeah. So this same chemistry that we use to make a fancy dress can be made, for example, on a T-shirt that can be sent to a person 5,000 kilometers from here. There are no doctors. And then the doctor sends, okay, use this T-shirt, connect to the internet, and then all the information from your body, the doctor can actually see it on the computer. And then say, oh, I can see what's happening to you. In some countries, it's like that. You don't have a doctor. We are in the US, we are spoiled, yeah, because or in Canada, we can go to a doctor very easily. But, well, in some remote places, you can, yeah?
So, another question, where were you in all of this, say, 2 years ago?
So 2 years ago, none of the color ones were possible. We did the changes in UV, the counterfeits. So every year we keep adding, yeah. And that's what we would like to change the fiber industry to make sure that textiles are no longer just a piece of cloth that gives you a sense of personality or cover your modesty, yeah? But also provides you a function. As a chemist, I don't see this as a jacket. I see it as a huge surface that I can use for something else. So if I want to eat on the street and I'm concerned about bacteria, I just clean myself. If I go with this jacket to a Cornell versus which one is blue? Duke University game. I may not be welcome, yeah, on blue. So I just changed the color of my jacket to red, yeah. And then I go to a party, and then people throw me, they were drunk and throw some wine on my jacket, then I'm able to take it off. And then it will not smell, and I don't have to wash it. No washing is very important to me because I don't like washing.
Yes, but how can you make inroads with the present manufacturers of clothes and cloth?
Yes, so every time there is a change, there is a new change of knowledge. The traditional players don't want to play, yeah, because that affects their baseline. Mm-hmm. But I will argue that you can make even more money with new applications if you have this type of functionality. We have been doing this for thousands of years. For example, washing. Washing is a concept I have a bias because I don't like washing. My wife hates when I say this. But if you look, for example, the first written material came from a group of people called the Assyrians, the Assyrians, in the border between Iraq and Iran. They were the first one that documented some of their behavior. And you look at those stones, and there is a person washing the clothes, in the river with a stone, This is 5,000 years ago. We keep doing the same way, except now we use a washing machine, water and mechanical agitation. Same process, nothing has changed. What about if your clothes don't need to be washed? Say they don't smell, they don't stain. So why do you need to wash them? So these are the ideas that are on my head.
Yeah, but the washing machine manufacturers are not going to like that.
5 years ago, I was in Amsterdam, and I gave the same talk, and the guy asked me the same question, and then he told me after I answered, he says, I was going to invite you to Brussels to give a talk, but now I cannot, because I'm the president of the European Association of Washing Machine Manufacturers. So you kind of put out those business. And there are other major brands that tell us, can we license Cornell patents so nobody else will use them? Because that will affect their businesses. Yeah, if I were to make money, that's something that could be possible. People buy patents to prevent others from doing. But we at a university, our goal is to make new science, new knowledge, and especially educate the next generation of scientists and designers. So people like Abby, for example, that can think in these two worlds, those are very unique skills. The big companies operate like that. Apple doesn't have these divisions, or Google, or they have this very perfectly oiled machine to have people with diverse backgrounds that can come with new ideas. And that's the value of diversity. This country is blessed because people are from different backgrounds. And if you look at companies like Facebook or Google, they're countries that produce more computer scientists than the US, more computer engineers. But these companies could only happen in a place like this. But we just make little things. That's what I tell my mom when she asks me, what do you do? I say, I do small things, Mom. So,
That's always been the Cornell tradition. When we were here over 50 years ago, we were encouraged. You want to take something in ad, you want to take something here and there, we'll accommodate your program.
Mm-hmm. And I have students who are religious studies. I have a musician who is my best computer programmer. The kid goes, he's very quiet. He just goes, his name is Alejandro. He just goes, put his headphones. That's the programmer, And I have also people who want to be doctors, MDs. I have one patent attorney who was a chemist before. So if you guys came for the 150th anniversary of Cornell? No?
I've been to one in Florida.
Okay. So there was a big exhibit of huge images. It's called, Illuminating Science. One of those images was taken by my student who was a patent attorney. But at that moment, she was a chemist. And she was so excited, so happy She should, yeah, because.
Yeah, they showed that in Florida, event that I went to.
Okay. So one of those images came from my group.
So your electron microscope, you said color has no meaning, and I understand that, but the astronomers essentially use a color palette as a means of identifying bits of the images they take with radio
Yeah.
telegraphy. So is there any use in your world of doing the same thing or not?
Yeah, we could do color of these images that are taken with electrons, but we haven't advanced too much on that because we think that by adding color we might be able to distort the information that we obtain. Maybe it's just the pure material scientist inside me. But I'm going to show you an example because last year I was asked to work with a designer. And then to create a combination between science and art. And I gave her some images, and what she did is, let's see where she is. Yeah. What she did is, in science, I like to have scale bars, like little numbers to tell me this is the size to relate to. But she was an artist, and she didn't like that. So what we did is, I gave her the ideas, and then I told her, you figure out how to do it, and we have a huge argument. And at the end, she was right. She told me, how can you do science without numbers? And let me show you where it is. Let me put the sound. Oop. Where's the sound? This is not gonna. Okay, so this is the one. Listen. So she made this for me, so it has numbers, but it looks nice. We call it nanoware. And it's sponsored by the Council for the Arts, yeah? And then she did this for her without numbers. My favorite.
What are you down to at that point?
So this was the artist. And then we have an exhibit. So she made my images look beautiful. without numbers, yeah, and music. And so it was, I have to say that by interacting with people like these artists and the designers, I became a better chemist, yeah? And I also think that they became better designers by interacting with someone. But you have to be patient. It's not easy because we are so different. And if we respect each other's skills, things will work out. I will argue that it's as difficult to design a building as complex as it is to design a dress or to design a molecule, yeah? So these are different, or design a piece of jewelry. They are different skills, but if you have the patience to talk and understand what the other person is trying to achieve without judging, without opening your mouth and saying, you are crazy, which I never said, I just thought about it, then you give the chance to these collaborations to happen. And because that's the other part. Once you say no, or this is not possible, or this is not going to work, it's too difficult, that person will never ask you again. There's a big chance, yeah? And then you miss all these opportunities, yeah? And if I say to the student, I'm sorry, I'm too busy trying to get my tenure, this is not going to work, she may never come back, yeah? And I never have the story to tell. So it's an issue of patience, and I have very good professors when I was in school. And I just, every day I ask myself if I'm as good as they are. So, and professors will always be as good as the students, yeah? Students are the real product that we develop, yeah? So, any more questions?
Actually, one quick
Yeah,
question
sure.
about the insecticide. On the, I guess it was like a cape almost. Did it smell, the insecticide?
No.
Oh, okay.
It didn't smell. That's the good thing. It didn't smell because it's actually captured inside the cage. Only when it opens, it smells.
Okay, because we have these insecticide bracelets that my dad bought, and they smell very powerful, like citronella or something. And my brother had one on during the 4th of July, watching the fireworks, and it upset my mom. She had to walk away because her eyes were
Oh, I
watering.
get
So I'm
headaches
wondering
with citronella,
if
yeah.
there's a way to do bracelets that don't smell.
Yeah, so it's similar concept to Fabrice. You guys know Fabrice, yeah? So it's
Yeah.
Fabrice is made with a molecule called cyclodextrin that captures some of that smell, but it can also capture the insecticide.